see what you're saying.
I think before we jump into the mapping magnetic field lines with Laura, I just wanted to do a quick follow-up about our teleconference or our Zoom conference last month in July with the Van Allen probes presentation by Dr. John Bunnell here at the Space Sciences Lab. And I know that some of you were interested in doing a follow-up with that, with John, and learning more about how to access the Van Allen probes data. And so Don Turney and I were talking about setting up a separate meeting so that those of you who follow up on that, we can arrange that for you. And Don, I don't know if you want to say anything more about that at this point.
No, that's it.
Okay, so of the people who are on here, how many of you would be interested in doing a follow-up with John Bunnell and another Van Allen probe scientist to learn more about how to access the data? Okay, so I see Vic. I'm going to write this down. Vic, Lynn, Laura,
Nancy, okay.
You can answer it in the chat.
That was what I was going to suggest, is put it there. Good minds think alike, Ricky.
Yeah, great idea. So if you are interested, please let me know in the chat, and then Dawn and I will follow up with you separately. Thank you.
Nancy, I have a question. If you miss it, can you still do a follow-up, or you cannot?
Great question, Phyllis. Thank you for asking that. And yes, definitely you can. So if you missed last month and you're interested, first of all, I would say that let's talk separately to catch you up, because if you missed last month, maybe you don't know whether or not you want to do a follow-up.
Okay.
And so, yeah, so if you missed last month and you want more information, then let's do a follow-up on that too.
Okay.
Are the recordings available yet? Because Phyllis could always watch the recordings from the last month too.
Yeah, the recording is available. The issue with the Zoom recordings is that they download in such a huge file size that the Wigio can't usually upload it because the file size is too big. So I'm sure that there's an alternate way that we can get that to you all, maybe through like something like Dropbox.
That's what I was going to suggest, Dropbox.
Something like that. But that would be the best thing to do for follow-up, for those of you who missed it last time, is if we can get that to you and it would come as an MP3 file, and then you could watch it and get the information. Okay, so I think with that, let's move into the main part of our meeting today, which is mapping magnetic field lines with Laura Peticolas. And I think you all know Laura, either because you've met her in person or because from the June workshop. So Laura Peticolas is the director of the Center for Science Education, which is morphing into Multiverse. We're changing our name from the Center for Science Education to Multiverse here at Space Science Lab. So she's the director of Multiverse and also a solar physicist by background. So Laura is here today to do the mapping magnetic field lines activity. And I'll turn it over to her and her two cameras. Laura and Ricky are have a system rigged up right now. There's one video camera to look at their faces, and another video camera to look at their desktop, their hands, so that you can both simultaneously see the presenter and see what's happening. So this is a bit of an experiment. And we'll see how it goes, but they tested it out yesterday, and I think you're in for a treat on this one.
Okay, so I'm gonna start with a presentation that's available to you all online. So I will at some point, or maybe Ricky will, at some point we'll put the URL for the presentation so you can get to it. It's a presentation.
Laura, it's also on the Wigio. It's also posted there already.
Oh, that's right. Wow, how much I forget in one day. Thank you,
There's
Andy.
a lot going on right now. You're good.
There's a lot going on, yes. Okay, so on Wigio, you'll find that. So I'm going to start with that. So I'm going to share my screen. And hopefully I will be able to get to it. You see it, Ricky? You know, I was having a hard time actually doing that. So there we go. Okay, so while I'm getting this up, it was right here. Now it's more.
Excuse me.
So I'm going to stop sharing for a minute, and okay. So I guess what we'll first do is, how many of you have taught magnetism in your class before? Okay. And so the first part of this lesson is to look at you have a whole bunch of materials where you can see if things are magnetic or not. Well, so that the students can see if things are magnetic or not. And I'm not going to go through that section, but instead I'm going to show you this presentation, which I now have open, which is so exciting because it was open. Now it's open again. Okay, and here I go. So now I can share this with you. If I can get back to here we go, Zoom. There you are. And now I will share screen. Okay, so those of you who are, do we have anyone who's just on the phone? I forget.
Phyllis is. Yeah, Phyllis is on the phone.
Okay, thank you.
And I just want to make a reminder that if you're a teacher, to make sure to mute your microphone. It's in the bottom left-hand corner of your screen so that there isn't any background interference in Laura's presentation.
Okay, thank you, Andy. So what you'll see is on the screen, Phyllis, I've just got a slide that says what is a magnet, what materials are magnetic, and then there's some pictures of various
And
materials.
this is based on your PowerPoint?
This is my PowerPoint, that's right.
Okay, got it.
Oh, do you have that there with you?
I was able to open it earlier, but for some reason I've been trying to get back to it and I have not. But that's fine, I'll find it.
Okay, so as you're looking, I'll just give a brief overview of what the slide shows.
And Phyllis is Nancy. I'll email it to you also. So if you have access to your email, you can pull it up that way or try.
Okay, that'll be good. Thank you.
Thank you, Nancy. So so the grade level, thanks Wendy, the grade level is somewhere between, we've had, it's targeted at 8th grade, but we've had teachers modify it for 4th grade, and we've had teachers modify it for 9th grade. And I think some of it has also been done in physics courses, which can be 9th or 12th, depending on your school. So I don't know if anyone wants to say anything about, because I know a few of you have actually used this lesson before. Yeah, so Vic, thanks, 9th, 11th, and 12th. So I'll give you time, there'll be some time here as we go along to add what's worked and what hasn't worked. As part of this lesson also, which is online, there's a section for having the students work with the different materials and look at what is magnetic and what is not. And in that, typically, the students, we make sure to have some, a wide variety of materials. So what do you expect, for those of you who maybe, I don't know, anyone really, what do you expect, what materials end up being magnetic? Does anyone want to comment on that? Or also, what do your students expect to be magnetic?
The students expect anything that's metal to be magnetic. So they'll throw different, we'll have a box that has all kinds of maybe wire, like you have on here, paper clips, nuts, bolts, all kinds of things that are metal, and they just expect that everything that's metal is going to be magnetic.
Yeah, and then what do they discover with your kit?
Doesn't quite happen that way.
That's
They
right.
get really surprised with, with coins that are not magnetic because they assume that they're magnetic.
That's right. Yeah, I think also it's been interesting to see that when we've had copper in there, that copper isn't magnetic, especially for anyone who's used copper with electricity running through it, and then it is magnetic. So we try to always have something with copper in that activity as well. So I think that's pretty typical. People expect all metal materials to be magnetic, but in fact, the only metallic materials the only metallic materials that are magnetic either have iron, cobalt, or nickel embedded in them, or a combination of all of them. So also a part of it is just to make sure that the students understand that magnets also repel one another, not only attract. I think most students are pretty familiar with magnets on refrigerators, but depending on the grade level, they may or may not be used to the to magnets repelling. So we try to have strong enough magnets that will repel. These kind of do. You can kind of see maybe down here. This is where. Maybe I'll wait to do a demo on that. I'm sure you've all experienced that. So we have the other. So that's an important part of this, is just to make sure that there's some experience with that. And then the other thing that I've noticed both with teachers and students and the public is the terminology can get confused in terms of, in magnetism, what we're talking about are magnetic poles. And so magnetic poles, like poles repel, opposite poles attract. A lot of people tend to call poles charges, which is what you get with which is the correct terminology for a charge. But magnetism, as we'll talk about a little bit later, is due to charges moving, but it's not itself a charge. And so it's really important to keep the terminology separate from, when you're talking about magnetism, to really focus in on the fact that those are poles, not charges. So I think that's, I don't know if there are any questions at this point. I don't see any chats. Chatting is probably the easiest way to get a question out, and then we can unmute if you want. 26 chats. Right, are any of those important to me right now? Okay, no.
Laura, and I'm watching the chat window too. I'm sure Ricky is too. So
Okay.
you're good.
Me too.
Thanks, Don.
Good, good. Okay, so we've also in physics and magnetism, the concept of force is really important, and a force can be thought of as a push or a pull in a very simplistic manner, but that's fundamentally really what it is. It's just that pushes and pulls don't always happen when you don't always have to touch something to push or pull. And a force field kind of is the pattern in space describing how that force is felt by the object that the force is working on. So for example, and they're fundamental forces that come from fundamental properties of matter. So gravity, along with gravity comes a fundamental force, or along with mass comes a fundamental force called gravity. And you can draw what that force field looks like with arrows. And this is a vector force field, and so it's very simple. It's shown kind of in that box on the bottom left. And all the arrows point straight down towards the object of mass. Oh yeah. Hold on, we got to plug my computer in, or it's going to crash. Hold on. Where are we going to plug it in? Oh, yeah, we'll plug it in. I'm sorry. Quick. Thank you. Okay. And so gravity is a pretty simple force field. It's just, unless you get out into space and look astronomically, then it can get warped just like other force fields. But close to the planets, it's fairly simple, just facing down. And then, so if you put any mass in that force field, it'll essentially follow the arrows. It'll get pushed in the direction of the arrows. So electric fields work, we can look at what an electric force looks like, and just like magnetic poles, electric force fields, if they're they surround charges. So if you have two charges that are similar, like two positive charges up in this top right panel, then the force field, it can be drawn in such a way that you can see that they're being pushed apart, so the lines don't intersect. So if we were to put a little test particle in there, it would move, and it was a positive one, it would move away from the positive charge. So that's what those little arrows are saying. And then down below, you have a negative charge and a positive charge, and the force field goes from the positive charge to the negative charge. So if you put a little test charge that didn't interact with either of those charges, which it would have to be much less charged than those two, it would follow these lines. It would be pushed from one to the next. So for magnetism, we want to do an activity that, what does the magnetic field look like? So the Van de Graaff's a great way to show the forces. Yes, that's a good point. Vic, do you want to say anything more about that before we get to the mapping activity?
Well, especially for my freshmen, the idea of a field is really not in their idea of what's going on. Everything has got to be touching. And so if you go into magnetics and use the concept of a field, I'll use my Van de Graaff, and I'll use them perched on top of milk cartons and things like that, and they can actually feel that force field. And from there, then I go into the magnetism.
That's really nice. Okay, so maybe you can wait one sec. I'm going to now go to the, I'm now going to go to the activity part. So for those of you who have for those of you who have your materials, if you could pull them out, that would be great. So you should have paper, pencil, compasses, and magnets. And okay, did I stop sharing? I'm trying to stop sharing. Did that work? Okay, good.
Yeah, you stopped sharing.
Okay, great. So I'm now we're gonna mute this computer and go and turn on unmute the computer that has the materials. So hold on one sec as I do this. Unmute. Okay, great. So it looks like now the main is the material stuff. Is that correct?
Yes, that's correct.
Okay, wow. Thanks, Ricky. That went very smooth. Okay, so first we set up our paper. We set up paper, what we call hamburger style. So a teacher taught me that. So the two pieces of paper, portrait style next to each other, and then you tape them together and on your desk. And then what you're going to do is take one of your magnets, and you're going to move your other magnet away from your desk. So I'm moving our other magnets off the table.
Laura, this is Nancy. I'm going to interrupt for a moment. So I think that periodically it's bouncing back and forth on the screen between your video camera, and I think that there might be some background noise from Phyllis calling in. So what I'm going to do is I think that I have the ability to mute Phyllis's audio on our side. So Phyllis, if it's all right with you, I'm going to do that, and then I'll unmute you when there's time for questions.
Okay, that's fine.
Okay.
Okay, so thanks, Nancy. How many of you have your materials there with you? Any of you? Okay, good. One, two, a couple of you. Okay, great. Awesome. Oops. Depending on if you look at this camera, this camera. Okay, so this is actually, nowadays, when we do this in the classroom, we used to do overhead projectors, but now more and more when we go into classrooms, they have actually just what we have right here, a camera pointing down at a board. So this is very similar to how it's done actually in the classroom, but you can also use an overhead projector to model this for the students preferably before you hand out the materials. I'm sure you all probably figured that out, but so I'm going to model for you what we're going to do to make the magnetic field lines around this magnet visible. So we put the magnet here on your paper in the middle, and then actually tape it down because otherwise it'll move around. And then we have our compass. Okay, so is red north or south? We'll hold on to that question till we get the mapping done, and then we'll have a conversation about that. But your compass needle, let me just tell you, should be pointing to the blue side. And so if your compass needle does not point to the blue side, which will happen when you do this activity, after the first time you do this activity with students, there will be some compass needles that end up pointing to the red side. And that is because students love to play with compasses. Oh, my magnet's only red. Okay, so that's fine then. For you, then just wherever, that's very interesting. So what you might want to do for your all red compass is maybe color some blue on the part that the compass is pointing to. So I'll just try to hold this up a little closer here. Okay, so do you see how it's pointed to the blue? And then if I bring it all the way around, whoa, then it points away from the red, towards the blue, away from the red. So that's the convention. So anytime you talk to magnet manufacturers, that's what they'll expect. If your compass gets mixed up, then the way to change it back is to hold either end of the magnet over the compass. And you have to keep the compass needle from moving, and then which is not easy. And it's especially not easy when I'm trying to hold it this close to the camera. But I'm going to stand up to try to make this possible. So you try to keep that steady. Let's see if did I do it? No. Okay, and now see how it's pointing to the red side. So it takes some practice to get this to work, but essentially what you're doing is you're realigning all the little domains in this compass needle. So, all right, so now there's the blue. And then each student gets a compass. So Ricky, maybe you can come over here and join me. I'm gonna bring your chair over. Okay, so Ricky gets a compass and I get a compass and the teacher has a compass. So what you're gonna do is you're gonna put let's see, pencil. Also, you have to use, it's best to use pencils for this or pens without any metal on them. So when we were first doing this, we realized that we were using pens, or teachers were using pens, or that had metal right on the edge here, and that was then affecting the compass. So pencils are the best, but like this pen has no metal on it, so I'm going to use it. Can you see that? Oh, there. Also. So you just draw a dot somewhere on your page. So Ricky, just pick a dot somewhere. And then you're going to put your compass right on that dot. And then you're going to put a dot right next to the compass, right where the arrow is pointing. And then you're going to pick up your compass and you're going to move it to that next dot that you had just drawn. And right in the middle, so the dot, you can't see the dot anymore because it's right over the middle. And then you're going to, again, put a dot right where the compass is pointing, right next to the compass. And the key here also is to keep the dots fairly close to one another. So you have to have a compass that is pretty small, like these, that I got at Arbor Scientific. Not that I'm endorsing Arbor Scientific, I'm just letting you know where I got them. And then you move it to the next dot, and then you wait till my needle's wiggling a little bit, so you wait till it stops wiggling, and then you put another dot, and you move it, and you put another dot, and you move it, and you put another dot, and you do this until you go off the paper, or you run into the magnet, and then what you'll do is you'll go back to the original dot, and you'll follow the tail. So you see this line went to the magnet. And then I'll go back to the original dot, and now I'm going to follow the tail in the same way I followed the arrowhead before. So I put a dot where the tail is next to the compass. And so I'm making all these dots. I'm following the compass direction, the vector in the force vector field. And we're trying to make it visible, and we're just randomly choosing places on our paper to make this line visible. So it's good to have 2 people per page. And then what you're going to do is you're going to connect the dots like this for mine. And then I put the compass back on to see which way are the arrows pointing. I'm going to draw the arrows here. Okay, and then you have the students do more of that. So they pick another dot. They put another dot randomly on the piece of paper. So I'm going to pick one right up here. I'm going to put my compass on there. And I'm going to do exactly what I just did. So, I'm going to draw my line. And as I'm doing this, I just want to mention that what you and your students are doing when you're doing this is exactly what scientists do when they model magnetic field lines with computers. So they will have a whole complicated computer model of Earth's magnetic field, and they'll want to make visible what that looks like on the computer. They'll want a visualization of that on their computer, and they'll tell the computer to pick some spot randomly within that computer simulation, and the computer will then do exactly what we just did. It'll move a little bit within the space and find out which way the magnetic field is pointing, and it will move the same amount again. And that's how they create these field lines in those computer simulations you may or may not have seen of the magnetosphere. So I like this activity not only because it's interactive and it's making something invisible visible, but it's also duplicating, replicating what scientists, a practice that scientists do when they are modeling magnetic field lines. So I'd like to just take a moment while we're making this for people to go off mute who have done this and talk a little bit about how they've done it in their class and what's worked and what hasn't. And so Laura, or I saw you put something in the chat. Do you want to share unmuted a little bit as we continue to draw lines here? Oh, well, your mic's still not working. Okay, so for Laura, we have to read her chat, which is great.
And Phyllis, I unmuted you too, so if you have a question, you can feel free to ask.
Okay. I would have loved to see it. Is there a way that you can send, download a copy for me to actually see the activity?
So Phyllis, what we're doing is recording the Zoom right now, which will include the video part of it.
Okay, okay, good.
So yeah, you will get to see this.
Okay. I got lost when we started adding the dots because, of course, I'm not looking at the video, but I think it's interesting that lining up the magnet with the compass, and I was able to see the movement that the professor was talking about.
Great, that's great. Yeah, I can see how without seeing what I'm doing, it's probably hard to replicate. Do you want to say anything about what's worked, or Wendy? Also, I know you have.
Okay, Laura.
Yeah.
I'll flash some of my students' works that they've done. I've got a whole section of them around here. If you're interested in seeing them.
Yeah. That sounds good. Yeah. Why don't you start showing those?
Because there's the basic simple one that starts off. And we still have somebody on the phone.
Yeah, they just got muted. You're good.
Yeah, but they're still on the phone because my screen doesn't show up. All I see is a phone.
We can see you, Vic.
Okay, so you've got the simple bar magnet, but the thing that a lot of the students get fired up about is once they get the idea Then they start doing their own thing. For example, here's 3-bar magnets. Or you end up with a circular magnet,
Oh, cool.
the ring magnet. Or horseshoe magnets. Or horseshoe and a bar magnet. And there you'll see some real interesting combinations of polarity. And then for the real smarty pants who think they know everything and they don't need to do this because it's too simple, before they do it, without them knowing it, you tape a couple of them underneath their table. So there's what they think is going to happen isn't. And then they kind of go bananas for a while. And then eventually, if they are really on top of things, they'll figure it out and they'll look underneath the table. But it's, to me, I had seniors do this. And you get the results of the idea of a field. Because to me, that's the piece that this magnetism for my classes is, this concept of a field, whether it's gravitational, electrical, or magnetic. The field is the piece that most kids can't fathom because they know touch, but they don't know fields. And so I usually use this whole magnetism with freshmen, my 7th graders, even my physics students. We'll do some of this just to get a sense of a field.
Vic, I think that you taught, I think it was you and Laura that taught me in Alaska my first year when you put the 2-bar magnets next to each other and then you flipped some of them upside down, and it kind of modeled the way when the sun's magnetism comes at the Earth, and sometimes it interacts with the Earth's magnetic field and other times that it doesn't. Was that you that taught me that?
I can't remember.
Oh.
It's been, I can remember Alaska, and I can up in Anchorage, and I remember doing it, but I'm having trouble remembering last week. But I believe so. We've done, Laura and I have done this a couple of times for a couple of different places.
Yeah, Wendy, do you want to add anything? I know you have experience with this.
I've done it with all, I guess, 9th and 11th and 12th grade. And I used the butcher paper, not butcher paper, but freezer paper. And I think I don't think if you put one magnet on there and you have them on all 4 corners of the paper, you could have everybody going at it at once and get away from the magnet, and then you can see the field lines veer off as they start doing weird things. They start getting away from the magnet's field and start lining up with the Earth's field. So I thought that was cool when they saw that.
Yeah, I've had a lot of teachers make that point, that if you get a big enough paper, you'll start seeing field lines just all going off in one direction, pointing north, to the North Geographic Pole. Because, of course, Earth is a giant bar magnet. I mean, it's not a bar magnet, but it has magnetism in its core due to actually liquid iron and electrical currents. And so the compass points north. If you're far enough away from other magnets. Terry Parent tried to do that in their gym. He was one of our teachers, and he found out that there were big rebar underneath the whole gym holding up the floor, and so they got these crazy patterns of of lines basically then going towards the iron in the floor. So I don't know, Wendy, where you go to do the big paper so that you can be successful finding the Earth's magnetic field. You just do that in your classroom? Oh,
Yeah, we just do it. Yeah, we just do it in my classroom.
Yeah, and that works pretty well.
Mhm. We still do that. We still do that one thing. I think everybody should with the jump rope. where you jump rope out. Remember that, you guys?
Oh, yeah.
Get that current
do
to flow. They love that. When I show them that, those seniors, they're just flipping out. So that's something I think we could tell the guys, other guys to share.
Explain a little bit what that is, Wendy. Kind of just.
Vic, can you do it? You do better, Vic. Okay.
Sure. What you basically do is you get two students and a 50-foot drop cord. And then you hook up a, usually an ammeter, or it's got to be a small ammeter to the drop cord. And then you start twirling it like a jump rope. And as it goes through the Earth's magnetic field, it generates electric current.
And then the ammeter needle moves back and forth.
Yeah, as it goes up and down, and then you start having them adjust north and south, and they can change the varying amounts of current as you get a more direct perpendicular cut of a magnetic field. You get a bigger jump. As you go more and more parallel, you get less and less. And so you actually can start playing with the idea of induced magnetic fields and generating electricity, only you're doing it on a big scale. They get a kick out of that one.
That's fun.
Yeah, and we can all of those lessons are on a website where we'll link you to that website soon. Claire is not on today. She's giving a tour of our lab to some folks, unfortunately. So why don't I go back to so there was a question about north and south. So one of the things we also like to do, like you saw on Vic's, thank you, Vic, for bringing the classroom models or classroom, I forget what that's called, but classroom samples, that's what I'm trying to say. You saw that they had drawn around the magnet so that when you take the magnet off, that there's a memory of what was there. And then if, for those of you who have the all red magnets, if you just draw part of it, you can just draw the whole thing red. And the area where these vectors are pointing, they're pointing to the south magnetic pole, and they point away from the north magnetic pole. So that's the convention, is away means you have a north pole, and towards means you have a south pole, and that south magnetic pole. So that's the convention for colors, and also for the direction of the needles. Are there any questions on that? Okay.
So this is Nancy. I have a question because I think that the teachers all received the magnets that are red because the teacher source where it was ordered from, I don't believe, carries these magnets with the red and the blue anymore. And so on their website, they say that the side with the dot refers to the North Pole. And I just want to double check with those teachers who are using it now. Does that match? Is that correct? Is it really that the dot side is the magnet's North Pole?
Yeah, that's what mine has.
Thank you.
Yeah, and it should point to the south. That's right, Jane. The dot is north, and it points, the compass points to the south.
Okay, thanks. I just wanted to double check on that because I know that this can be confusing, and I just wanted to make sure that the information on the website was correct.
My magnet has a north and south on it.
Oh, great.
Can you see that?
Yep. Great. So you'll want to make sure that the arrow's always pointing to the south end. That's really important. So what that means, of course, some students will recognize that, but wait, the compass points to the north geographic pole. Well, it points north. So what's up with that? So it's the magnetic pole in the northern hemisphere happens to be a south magnetic pole. So the magnetic pole is 180 degrees opposite from the rotational pole right now.
Laura, may I make a suggestion?
Yeah.
And that is, when I just start this out, versus trying to convince kids that the North Pole is a South Pole, I'll simply look at a compass and say, okay, this is the north-seeking end of the compass, and this is the south-seeking end of the compass. Once they've got the idea of a magnetic field and how it works, then you can say, so that, what is that north-seeking end of a compass really, what is going on?
Mm-hmm.
They'll get the flip. But to start right off the bat to say, well, the north magnetic pole is the south pole, screws them up pretty good.
Yeah, that's a great point. Mm-hmm. And Laura, I see you say, yeah, send them outside to use a compass. Yep.
So just to clarify, if I were to look at a globe where the North Pole is, it's really the south magnetic pole. And where Antarctica is, it's the north magnetic pole, correct?
Got it.
Okay.
Yeah. And it's not, depending on what grade level and what you're doing with this, it's not, the students don't have to get to that, I don't think. I think what Vic was saying earlier about this being a vector and, that magnetism is a vector and that this is a force field and it, if you put a magnet on here, it'll align with this force field. And that's what we're essentially doing with the compass. We're putting, well, I don't have a magnet there anymore. We're putting a little mini magnet in a big magnet force field, and it aligns with that force field. It is being pushed and pulled by this invisible field, and it has a direction, it has a strength to it. So that's really I think the main points for this. So if we go back to the PowerPoint, is there anything anyone wants to share before we get back to the PowerPoint?
Once you've done one of these or two of these, it's also a nice little side note to give the students, say, okay, this is what it's going to look like. You're going to get two magnets. Predict what the fields are going to look like. And then have them do it. It's kind of get the idea, okay, predictions, then activity. Predictions, then activity. To get the idea that a prediction is an important piece of this, not just, well, let's have fun and draw lines.
One of the extensions that I do with my kids in the past, and I have a couple of them here, not kids, but stuff, is I put cow magnets in soft balls, and we have a frame that we use at school. We use it usually for pulleys, but I use it for this. Anyway, they suspend it from that, but before they do that, they map out. They give themselves an equator and they give themselves a prime meridian, so it becomes a full four XY axis. And they do this on old-fashioned overhead paper because we have boxes of this stuff, of the old overhead film that we don't use anymore really in the classroom. So it's mine. And so anyway, I have the kids plot out their magnetic field for their x-axis, and I have it suspended so their y-axis, and they end up coming up with something that looks like this. And so we cut it together on the axis. We end up, and what we do with it is they get to the wall and they take a flashlight. We have the room darkened. They take a flashlight and they shine the flashlight at it at an angle, and they're able to project the image of the 3D kind of thing onto the wall. We can't use the iron filings to do a 3D imaging of it because our school district won't let us have the filings. So this is what I did to try to get them the idea that, certain planets do have magnetic fields. So they're able to project this on the wall. They get a really big kick out of it because it's something new and different that they've never seen before. So anyway, it's a lot of fun to do with them. And this is just when I ran to the closet real quick to go get it because I didn't realize that I had them at home. So that's one of the things that we've done with it to extend it a little bit further.
That's so cool. I love that. Oh my gosh. Oh, you can see Claire. Wave, there she is.
Hi guys, sorry I'm intruding. Sorry I can't make the meeting. I have your
Okay, I'll come down. Okay, great. Okay, so I'm just going to go through a couple slides here, and then I'll be finished. So you can see here the magnetic field mapping that we just made, magnetic field, so you can see that magnetic fields always come in a dipole field, which means two poles. Unlike charges, electric charges, you can have a single electric charge out in space. However, for whatever reason, you always have two magnetic poles. And actually, there's a good reason for that, but we'll talk about that maybe. And we just talked about Earth being a huge bar magnet. So moving molten iron in the Earth's outer core causes most of the magnetic field. And these magnetic fields are not aligned with the geographic poles. They wander and flip and move, and they're very dynamic. So then I just have there was the jump rope generator you all talked a little bit about, which is a good way of seeing that you do have a magnetic field on Earth and you can actually use it to generate electricity, even though it's just a tiny, tiny bit. And there's more activities in this guide that we have where you can actually have the students work with electricity and magnetism. So for those of you who want to do that, you can look in there. And so these slides just show a little bit more about what to expect with electricity and magnetism. Both that if you have moving charges, you get a magnetic field, and if you move a magnetic field in a wire, you can generate electricity. So you have this interesting kind of interplay between electricity and magnetism. And in fact, electromagnetic radiation is made up of a dynamic electric field creating a magnetic field. So not only do electromagnetism is at play in light itself, which is pretty cool, I think. And of course, we know electromagnetic radiation we have creates light and of various wavelengths, even wavelengths you can't see. So there's often this question of, and I'm going to skip forward to 3 slides here for a moment, what's going on in a bar magnet? And so this is a slide that just shows that you have, when you have elements like iron and they form solids, they form a crystalline structure with these things called little domains of many, many atoms. And if that iron is in a magnetic field, as it cools, those crystalline structures will line up with a magnetic field that it's cooling in. So these domains then start to line up with one another. Each domain's like a little mini bar magnet. And even if you have iron that isn't in a magnetic field when it cools, so like a nail, for example, it has all these crystalline structures with little domains and many atoms all aligned magnetically with one another. And you can then align all of those mini domains into one giant magnet in your nail by putting an external magnet outside of that nail and forcing those domains to line up. And then that's how you can get a bar magnet. Or you can work with intense chemistry, and so this is what the bar magnet manufacturers do. They've come up with ways that the domains can work together to form the strongest system of domains that won't get perturbed when you drop the magnet or change it, that they'll stay aligned with one another. And essentially, within each of these atoms, within each of these domains are these iron atoms, and in these atoms you've got a nucleus made up of quarks, which make up basically your neutrons and protons, and you have electrons. And electrons are charged particles, and they also have something called a quantum spin. And so in essence, they move, they spin, but they spin in a quantum mechanical way. So they're not actually spinning. You can't kind of see them spin. But this spin, because it's a charged particle moving, or a charged particle with a spin, it has a magnetic field. So these electrons have magnetic fields, and they can add up with one another within the atom. So this is why iron is magnetic, but other atoms aren't, because essentially what you have are these electrons out in a particular shell in that atom that all are pointing in the same direction. They're unpaired electrons, so they don't cancel each other's magnetic fields. Instead, they add up. Their magnetic fields add to one another. So you can see here, you've got these 4 electron spins that are adding up to create a stronger magnetic field within at the atom level, and then that interacts with the other iron atoms, and they all kind of clump together with one magnetic field and creates that crystalline domain. So that's all I have for today. So are there any questions or comments people want to? I don't know. Nancy, how much more time? I saw you had the time. Nancy, Ali.
You can take a little bit more time. We have I want to go over the evaluation at the end, but that will really only take about 5 minutes or so.
I have a sun-related question that someone might be able to answer for me if we have a little extra time. I can wait till the end as well if that's better.
No, sun-related's good.
Okay, so the other night we were talking with some friends, and someone was saying, you know, that the magnetic poles on the sun are shifting, and that's not abnormal, and, you know, happens every so many years. But when those magnetic poles start to shift, apparently we don't get as much plasma ejected from the sun towards us. Is that correct?
Mm-hmm.
So is that possibly the cause of the more mild weather that we've had over the summer across most of North America? Or is that just a coincidence?
So the easy answer is it's a coincidence.
Okay.
That said, it's believed by solar scientists, let me rephrase that. There is some perhaps evidence, but people are looking at this more carefully, that when the sun is extremely quiet, meaning that in these flips, magnetic field flips on the sun, you have very few sunspots, and you have very little magnetic activity, and you have very little plasma being ejected towards us, that the output of the sun during that time is a little tiny bit less than in light than the output of the sun when it's really active. So actually, when the sun is really active, you have more light emitted from the sun as well as plasma. And so what they're finding, what they've seen in the past is during those, when you have a long period, many solar cycles. So a solar cycle is every 11 years it flips poles. So a whole cycle is 22 years. And if you have more than like 4 or 5 cycles, so 4 times 20, let's just say 2 cycles. I think Maunder minimum was 2 cycles. So that's 2 times 22 is 44 years. When the sun's output is less, then you can maybe start affecting climate. But it takes that long of the sun being at the same output for the climate to actually be affected.
That makes sense.
So in terms of a year-to-year basis, it's not really going to affect what happens over the summer. We are going through a time now when the solar maximums are less than they used to be. And so there's this concern that I've heard from some people that climate change, with all the CO2 in the atmosphere is heating up the atmosphere. But we happen to be helped just a tiny bit by the sun not being as active right now. But now as CO2 continues to increase and then the sun eventually comes back in like 20 or 30 years to really being active, then we could be in the sudden crazy time when we have the sun's output as well as our own putting CO2 in the atmosphere, and we could go from a bad situation to a really terrible situation. So we're kind of being given a little bit of time maybe to changes. I don't know.
Thanks for taking the time to explain that.
Laura?
Yeah.
I don't know if you can see this, but I'm going to show you this student work, and I'm going to show it to you really close, and see if you can tell me what's the matter with this.
Oh, yeah, there's something, they're missing some lines.
You'll notice it says north and south, and they are repelling each other.
Yep, they're not stuck.
Right.
Okay, here's another thing. I don't know if you've ever got one, but they sell a magnetizer that you can put a bar magnet in there and magnetize it. Again, that to me is a senior level idea. I switched to poles. Even though it says S, it's a North Pole. And it doesn't go to what they predict. And for a while, there's some confusion, but again, by modeling with that compass, they figure it out eventually. Hey, that N is not an N, that S is not an S. Something has switched. The idea of modeling and not getting the expected result, I'm looking at that as a very powerful junior-senior types of very simple projects, but screwing them up on purpose.
That's high-level problem solving.
Well, and that, again, if we get to think a little bit about the next generation science standards, the practices of science are so important in that, which is so great. And I think, Vic, you're totally hitting on the practices of science, which is, things get screwed up and you've got to figure out what's going on and create, either change your model or figure out how things got messed up. So that's cool.
And that's how I figure we can extend a very simple project that can be done by third graders, and they'll learn a lot from it. But you can extend this all the way through everything. And again, it's, to me, every level based on the instructor can make these more and more, shall we say, a learning environment for even the students that think they know everything.
Nice. Anyone else want to share anything, any other thoughts or comments or? All right. So I think Nancy, Ali, it's all you and the eval. Thank you all for joining me.
Thanks
Thanks
you,
for
Laura.
sharing all your great ideas too.
This brings back memories from Juneau.
Yes. It does.
We presented, had one recipient.
That was pretty funny.
Thanks, Laura, and also big thanks to Ricky and Claire too, because they helped figure out the setup, and Andy for testing it. So we've only got about 5 or 6 minutes left today, but I wanted to give you all a heads up about something that's going to be coming down the pipeline, which is the evaluation for your experience as lead teachers. And I think that I had mentioned early on that we have an outside evaluator. Cornerstone Evaluation is the company name, and Allison Walker is the company president. Many of you know Allison from other NASA-funded projects, and so she is the evaluator for the overall Themis project, and has put together a online evaluation survey for each of you to complete. And so this evaluation, there's a couple of purposes for it. One is to get feedback on your experience as a lead teacher in the community of practice. And so this is not evaluation of you and your performance or anything that you do with your students or anything like that. It's really an evaluation of the process. Since this is the first time that we've done this, you know, if we were to do it again with another group of lead teachers, or if someone, you know, in another division of NASA or someone else asked us, you know, what would the recommendations be, we want to have some external evaluation results to share with them. So that's one big purpose of it. And then the second one is, what are your recommendations for moving forward with the community of practice? And I'm sure you recall that we had asked for each of you to commit to being a lead teacher through the end of September 2013, with the hope that some or all of you would be interested in continuing on beyond that. And so now that we're approaching the end of the tenure of your commitment, we want to find out to what extent are you interested in continuing on, and what are your recommendations for expanding the community of practice. And so the evaluation survey will ask questions, and I'm actually going to share my screen so that you can see it. And this, we'll send the link out to you next week, probably on the 23rd, but I'm giving you a sneak preview of it here. So there's some introductory text, and then basically most of the survey is text boxes where you will write in your responses. So if you're the type of person who wants to think about your response first and before putting it in, I can also provide you with the questions ahead of time so that you can take a look at it. But there's questions about the overview of the current heliophysics community of practice, your perception of the goal and how we've met the goal, questions about expanding the community of practice, and then we get into some of these ranking systems of your experience, giving feedback on your experience of the community, of being a lead teacher, your contribution. And again, this is not, the intent of this is not to evaluate you as a lead teacher, but it's an evaluation of the program and the project. So the reason why we are going to be giving this to you in August, and the request is to complete it by September 4th, is so that we can take your responses as a group and use that to help plan the discussion in September about where to go beyond September. So really what we're planning to do is that Allison Walker will collect this information, give us the raw data on it, and we'll use it to look at what are some of the things that we need to prioritize to discuss in the September meeting. So this, the link will be emailed out to you. I think Allison might want to do it directly. So you can either expect to get an email from Allison Walker from Cornerstone Evaluation, or she might ask me to put it on to Wigio or email it out directly to you. So it'll come probably one of those two ways. And we're shooting for August 23rd to get it out to you, and then have you complete it by Wednesday, September 4th. And I think the last thing to add to this is that we are tying the evaluation, completing the evaluation as part of the task for the third honoraria, which will be processed at the end of September too. So so September 4th is the deadline. If it takes you longer than that, you can probably expect that Allison will be knocking at your door, metaphorically, and who knows, possibly physically. She's very determined. She's a great evaluator. So, so I just wanted to give you all a heads up about that this is coming around, and see if there's any questions about it at this point. Okay, so I'm not hearing any questions come forward, but if there are any questions, then let me know. And I think the final thing is that, let's see, our next meeting, our next monthly meeting is scheduled for Tuesday, September 17th. And I believe that we're still on the same time. I don't think we encounter daylight savings before then, between now and then. So it'll be the same time as today's meeting on Tuesday, September 17th.
I want to share one little thing on that time. Is my class schedule changed, so now I got classes. And I was telling the superintendent, I had the superintendent and the principal discussing it, what we were doing. Both of them said, we'll cover your class, continue working. So it does carry some weight, at least in our school.
Good to know. Thank you, Vic. All right. Well, I think unless there's any other last comments, thanks. It's great to have so many people back on this monthly meeting. I'm just so thrilled. I'm very sorry that Maggie wasn't able to join us, and Jim too. But it is exciting to see us all kind of come back together after summer, where people had different focus and travel and all sorts of different things. So thank you very much for joining us today. And we'll see you next time.
Thanks, everybody.
Bye. Thank you.
Bye.
Thank you.
Bye.
Bye. Bye.
See ya.
Bye.
Bye.
Everybody's leaving.
Bye.
Bye.